like in Hollywood. Okay, now we're recording again, and morning everyone. This is lecture 30. Last class we upgraded Hoeffding's inequality, which I'll remind you. So the scalar version, the scalar Hoeffding's inequality, which we did a long time ago, is one of the concentration inequalities that says something like this. So for any numbers ai, if I look at their randomized sum, so sum of independent random variables epsilon I ai, where epsilon i's are chosen as plus or minus ones independently with probability 1/2, so IID, independent and identically distributed, then the sum is sub-Gaussian. It's a sum of some sub-Gaussian, which means that the tail is basically it's e to the minus t squared. Normalized, so it's scaled by the variance, of course, where sigma square is the variance of the sum, which is the sum of the variances, and this is ai squared. So this was Hoeffding's inequality, very useful little inequality about randomized sums. What we did, we upgraded scalar Hoeffding's inequality to the matrix form. So now we have a matrix Hoeffding's inequality, which says that for any matrices, for any d by d symmetric matrices ai, a similar thing holds. So we look at the sum of epsilon I ai. Now this is a matrix now. Instead of absolute value, we take the norm, operator norm. And the right-hand side is about the same, except there is a factor of dimension d, t squared over 2 sigma squared, where sigma squared is something, it's the same, it's a sum of this metric, sum of ai squared, except of course it's a matrix now, so I have to take the norm of that again. It's an operator norm in both instances. This is Hoeffding's inequality. Good. Okay, that's what we achieved. This is a great result, a very deep result. And then we just look at this and we compare it side to side, like apples to apples here, this one to this one. And we see that the only real difference is this. This is our cost. The cost of the upgrade is this factor d right there. Is it big? Is it too bad, or is it good or bad? Well, it's linear in dimension d. I don't know. Is it good or bad? The real question is, do we have a curse of high dimensionality? Is it so bad that in higher dimensions this is useless and people or not? I don't know. What do you think? If you look at this, well, it doesn't look so bad, right? It doesn't look like exponential in D. That's good. It's linear in D. But in fact, the reality is even better than that. It only seems to be linear in D. But in fact, we should think about it as logarithmic. Let me explain this thought. The great thing is that this D factor, this cost, stays outside the exponent and not the inside the exponent. So in reality, the right-hand side, let me rewrite this inequality. Let's call this Sn maybe. Probability that the norm of Sn is larger than t. I'm just rewriting this, but I would like to bring that d in the exponent. So it's log maybe 2d minus t squared over 2 sigma squared. And when we do this, we see that the fact that the dependence on D is actually logarithmic. How does it manifest in practice? Let's say we want this probability to be very small, right? This is our exceptional event. We want this probability to be very small. So what do I choose here? Let me choose, well, you see these two factors, they fight each other, basically, right? We want this to be larger and we want this to be smaller. So let's choose T so they're about the same. Let's choose T to be, I think something like 2, maybe sigma root log D. I did that just so these factors are comparable to each other, if you equate one with the other. And so we get this, let's think this is 2D log D. So this will be $4D, let's see, 4 over 2 is 2, so it's e to the minus 1 over D. Would it be 1 over D? Yeah, or 2D maybe, log 2D maybe, something like that. Yep. So this will become log of like 2 log of 2D, and I think, yeah, that's good. And in high dimension, this is small. If think of D as being a large high dimensional thing. So that's very good news. That shows that Sn, the sum, is less than 2 sigma root of log 2D maybe, or log D, log 2D, with high probability. And that is amazing. That's perfect. Why? Because the dependence on D is logarithmic. It's a very mild logarithmically, the functions that grows logarithmically grows very, very slowly, much slower than linear or any polynomial or something like this, right? So that's our cost, the real cost of upgrade. The real cost of upgrade is this one, and it is logarithmic. Is logarithmic in dimension. And that is where the strength of this theorem is. And if if people, like 20 years ago, if you asked something like this, if that's true, people would say, we don't know, or maybe yes, but it would require a horrendous amount of work, like 30 pages of proofs or something like this. And now we have it. Now we have it in essentially the same way as we proved scalar inequalities. We just upgraded it perfectly. So that was a great chapter, success story of modern mathematics. Okay, so we do this with high probability. The next question we want to ask it should be, if this is with high probability, it should be true in expectation, right? The expected value, we want to show that expected value is less than that. It's believable, right? It's smaller with high probability, therefore the expectation is also small. Let's check that. So we would like to take expected value of Sn. How do we do this? What we know is the tail bound, like this, and we would like to take expectation. So here we will apply the integral identity, very useful one, that we studied for maybe in the second class, third class maybe, for any random variable, for any non-negative random variable z, you can take expectation by integrating the tail. Very elegant inequality that just connects tails and expectations. And we know the tail. Höfding's inequality gives us this tail, and so we integrate it, we get expected value, naturally. Let's do it. In fact, it would be easier for us to work with the square expectation squared. So I will do it this way, Sn squared, and then 1/2. Why is that? This inequality is always true, regardless of random variable. Let me just put it here, EZ maybe. For any for any random variable, this is true. But why? Anybody knows? Yeah, you should know. Hey, guys, you know that.
Is it like Cauchy-Schwarz for 2 times?
Exactly, it's like Cauchy-Schwarz. It's like L1 norm in the left, and there is L2 norm in the right, and the L1 norm is less. It's just hierarchy of these norms. L1, the LP norms, they increase. Right? The last one is L infinity, so that's why. So this is true, and therefore we would want to find this one. Let's do that. So expected value of Sn squared by the integral inequality. Let's do it. It's a simple exercise. It's greater than well, T is a bad letter here. Let's say S ds. It's greater than S ds. And we know it here. So S, so let's apply the Höfding's inequality for S being, for T being root S, I think. S being T squared. So we're applying this, literally I'm applying Höfding's inequality. So that becomes the integral to D e to the minus T square over 2, and T square is S over 2 sigma squared ds. Wonderful. Minus, yeah, I think it's good, right? And this is 2D goes outside. So this is 2D goes outside, and the integral of e to the minus function is this function itself. So I think if you compute this simple integral, you get 4 sigma squared d. Okay, that's bad. What did we do? What did we? You see how bad it is? It's d. What happened? Now it's linear in d. It's supposed to be logarithmic in d. Right there. We were hoping for something like this, logarithmic in d. We didn't expect linear in d. That's bad. And we did everything right. So how did it happen? What did we lose? What's going on here? The integral inequality is actually quite sharp, usually. Something is bad. Do you see what the problem is? How can we? Where did we lose? This is a huge factor. It must be that we did some sloppy job somewhere. There was some rough estimate that that ruined our estimate. Okay, how did we get this for 2D? From here. This is from here. Well, maybe this estimate is not sharp. Not always sharp. Let's check it for t equals 0. Check t equals 0. If this is 0, then e to the minus 0 is 1, right? And we have 2d. Is this a good estimate? It's a horrible estimate, actually, right? Because probability is always less than 1. We know that a priori, that's always true. And we got probability, which is supposed to be less than 1, is less than 2D. That's a very bad estimate for t equals 0, and maybe for smaller t, around 0. So that is where we lost a lot of error here, which suggests that instead of doing this silly thing around 0, just bounding 1 by 2D, we should be using the trivial estimate, that this probability is less than 1. Yeah. So for small t, let's just make this better. In this estimate, for small d, use the trivial estimate. Probability is less than 1. And for larger d, use the non-trivial estimate. How do we know where is this threshold? Where is small, where is large? Well, this is the threshold. As soon as the probability as soon as this bound drops below 0, it becomes non-trivial. Sorry, below 1. As soon as the probability drops, this bound drops below 1, it becomes non-trivial, and let's use it. If it stays above 1, it's trivial. Let's not use it. Let's use yeah. So let's do that. Let's do this instead. So what's a fix? So this is too bad. Use the bound, the trivial bound. Probability is always less than 1 for small s, and the matrix Höbning's inequality for large s. So let's redo the argument. This is from 0 to S0. This is our threshold of how small or versus large it is. Square greater than S ds plus probability Sn. I'm just breaking the integral into 2 parts. Nothing fancy happens here. And this one for small, I estimate by 1. And this for large, we estimate this by 2d e to the minus s over 2 sigma squared. You know what? For this, let's assume sigma is 1, just to make things simpler this time, just to check that everything is good. Okay, then we can bring back. So e to the minus s over 2. Okay, so this becomes, well, the integral of 1 becomes just the length of this interval as 0 plus, and the second one is 2d. Yeah, let's just think. If we integrate this, we get this. I think we get I think 4d e to the minus s0 over 2. Yep, good. And then we choose. Now we can optimize an S0. In fact, we can choose the best one, but it's clear that we already know what we want. So S0 is.
And why is it 4? Sorry.
Why is it 4? It's because of the change of variable involved here. Because of the
right.
If you do change of variable, you'll see. And so we choose S0 equals maybe 2 log d, for example. 2 log d. And then this becomes 2 log d plus, and the last term will just collapse. It will be just 4. Yeah. Great. Okay, we win. 8 log d. So now things are not linear, not polynomial. They're logarithmic. That's great. Fine. And I just did the last bound, assuming that d is greater than 2 for large d. Okay. So, and then that was for sigma equal 1, and for general sigma, we have squared 8. Sigma will reappear, so sigma squared log d. Do it yourself. It's a simple exercise to bring sigma back. Great. And if we take the square root of that, so expected value of Sn is less than expected value of Sn square and then square root, it becomes, well, 8, root of 8 is less than root 9, so it's 3, I think, less than 3, sigma root log d. Aha. That's perfect. This is perfect. It is consistent with this. We first proved that this holds with high probability. And now we proved that this also happens in expectation. So expectation is also bounded by the same thing, similar thing, 3 log d is 2 sigma, that doesn't matter. So the summary of this is that both in high probability and in expectation, the sum is bounded perfectly with just a logarithmic cost. Yeah, let's rewrite this. For any d by d symmetric matrices AI, we proved that Sn was the expected value of the sum epsilon I AI squared. That's, I'm just rewriting this, is less than 8 log d times, and now we remember what sigma was, sigma squared. Let me show you back again. Sigma squared is this. So I'm putting it back in here. Sigma squared. So sigma squared is AI squared. Ah, such a cute inequality. This happens for any symmetric matrices, and the way to think about this is that this is a matrix version of the scalar inequality. Let's think of scalar identity. Let's think of what for scalars it would be expected value of sum of epsilon I AI squared. Well, that's just a variance of the sum. This expected value of the sum squared, that's a variance of that sum, which is equals to the sum of AI squared. And now we have approximately the same thing, except at the cost of that's logarithmic in dimension. But now it holds for matrices, which is much more general. Let's just emphasize this one more time, that the cost of upgrade is logarithmic, which is great. It's very small. So we should be happy. Good. Any questions? What we did here with Hoeffding's inequality is very, very flexible. It could be done for anything, pretty much, for any other inequalities. Chernoff, Bernstein, Hoeffding, anything that you imagine. If you know some other concentration inequalities and probability, they will also can be brought into the metrics context. And we will do it, actually. We will upgrade Chernoff inequality in the homework, in the upcoming homework. You will do it by yourself. And I will just show you how to upgrade Bernstein's inequality without going through the proof, but we'll just guess what the form is, and you can do it yourself if you want. So metrics Bernstein inequality. I'll just try the metrics version of it. Bernstein's inequality, matrix Bernstein's inequality is about sub-exponential random variables, but let me state it for bounded random variables. So let xi be independent mean zero, symmetric D by D random matrices this time. In Bernstein's inequality, there were just random variables. We assume that there are sub-exponential, but this time let's do it simpler. Let's assume that they're just bounded. Let's say by one, by k, by some number with probability 1. So assume they're always bounded. Then for any t, the tail like this is greater than t, is less than 2d. The ideal situation is where the tail is like t squared over sigma squared, where sigma squared is the matrix variance. It's this thing. Let's call it the matrix variance. Just the analog, direct analog of the usual variance of the sum. And that's ideal situation, but as we know, for sub-exponentials, there is a mixture of tail. One is sub-Gaussian and the other is sub-exponential. So the truth is that it's a little annoying here to have this tail over k, where this is the shorthand for the minimum. This wedge thing is a shorthand for the minimum of the two. Usually the second term can be ignored. It's always small. So what's important in this is that the tail is sub-Gaussian, basically t squared or sigma squared, and the variance is the variance of the norm. So everything is pretty good. And the proof is similar. Just take the usual proof of Bernstein that we gave and literally put matrices there, just like we did last time. And you will do this in the homework for Chernoff, I think. Okay, any questions about this? Pavlo, you seems to be puzzled by something, no? Everything is good?
Well, I have a question that is might be like vague in general about the operator norm. Like we have these factors here appearing that is D, that is the dimension of the matrix. And so when we talk about for me, it's not obvious why any factor should appear at all, right? We have some sum, and we want to bound it. Like, why would the size of the matrix matter if we sum some matrix? So for operator norm, is there any intuition? Like, should we expect like D to appear for the size of the operator norm?
Yeah, exactly. That's a great question. I should be puzzled by that too. Yeah. That's a great question actually. Should D appear at all? Like we're so happy that it's logarithmic in D, but why would maybe there should be any D, any dependence on D? Why should it be here? Why should it be there? Why should it be anywhere? Here, for example. Maybe there is no dependence on D at all. And actually, there must be dependence on D. The truth is that there is an example showing that there must be dependence on D, and the logarithmic dependence is the best. And in fact, the square root of log is the best here. All of these factors, the factors that I put are actually the best. Or should be there, and we will do that. But we'll see that, but just not now. I would like to go from this to our applications next. One, to covariance estimation. And then we will clearly see that covariance estimation requires this oversampling factor. Otherwise, it will fail. And then backtracking this, we'll see that actually the D was needed in the first place. So that's the idea. I just wanted now to skip this and then return to this problem later. But it's a great question. Is it needed in general? Is it needed for nice distributions, and so on and so forth? It's a great question. A lot of effort was made during the last decade to understand when and if this term was needed, in particular by myself. There was many papers. Yeah, I will. So that's why, Konstantin. Yes, is there an intuition? I'd like to discuss that in the couple more classes. It will be very clear. The intuition will be very clear from the covariance estimation viewpoint, but I do not want to go to covariance estimation now to jump back and forth. Okay, just promise there will be. I promise I will. I'll come back to that question. But for now, it's just safe to be happy that this factor is not too much. It's just logarithmic. So people just say, okay, logarithm grows very slowly. That's fine. Okay. Thank you for this question. It was a very good one. Any other problems, questions, concerns? So, okay, so now we can just upgrade any inequality from random variables to random matrices. This is amazing. People, if someone saw this, let's say in 1999 or something like this, they wouldn't believe it. The intuition was totally against it. They would say, what do you mean random matrices here? What is the distribution of that random matrices? They should have independent entries. And I would say, no, it's a general result. And people would say there should not be any general result for random matrices without assuming anything about them, right? The entries that are not assumed to be independent. There should be, they're not, it's totally, any result about random matrices without assuming anything about their structure was thought to be completely out of reach, or actually false in mathematics before like 20 years ago. And this was a very big surprise that we can say something about random matrices without assuming anything about their entry distributions. Amazing. Okay, anyway, if we want this to be small, if we want the right-hand side to be small, then what t do we choose? We choose t to fight both the sigma square and k, right? So t should scale like, in the first approximation to the truth, it should scale like sigma, the larger one of sigma and k. And this is a maximum. We choose it just...
It's the same symbol.
Same symbol, should be maximum, yes. And maximum should be the opposite one. I always forget, yes. Thank you. It's a little wedge like that. So it should be the larger of sigma and k, so that t is able to scale above sigma and above k. Okay. It should be larger than that, so maybe c sigma and ck with large constant c, but it should also fight this d. If we bring it into the exponent, it should fight the log factor of d, just like we said before. So if you do things correctly, if you see what it is, then it's this choice is very good, where c is a large absolute constant. And in this case, we have probability less than 1 over d again, which is much less than 1. So this is a good choice for t. This means that the sum of xi is bounded above by something like this, with high probability. And also in expectation. If we redo what we did for Höfding's inequality on the previous page, we can same way, just integral inequality, break it into two parts. I'll not repeat that. We'll get this corollary that says that the expected value scales like this. Again, what's important here is that this term, the most important, right? Sigma is kind of the metric's standard deviation, which should be there, right? It's expected value of the sum of random matrices should scale like the standard deviation of that. That's expected. This is an annoying term. K is just a maximum norm of a matrix. Well, and we have the sum of matrices, so this is usually very innocent. the sum of matrices is and this term is just scales like one term, so that's usually very small. And the cost is logarithmic, which is very great. So this tool, matrix Bernstein's inequality, and in particular this corollary, is a very useful tool. And I just emphasizing this because we will use it a lot of times after, and you probably should use it too if you want, because it's so general. It works for any random matrices without assuming anything about their expectations, about their distributions. And the cost of dimension is very small. Okay, good. Any questions about this? We're done with theory now. That finishes our big block on theory, and now we'll go to applications. And the first one will be on networks, namely on community detection. Sometimes people say recovery in networks. So if you want to read more about this, the buzzword is community detection or community recovery sometimes. Okay, good. Let's do it. All right. So what's a network? We go back to our discussion in the beginning of this course, lecture 8, September 19th. A network is just, we just think of this as a random graph, undirected, so no arrows. Actually, graph, way random, just graph. G, to specify a graph, we need to specify the set of vertices and the set of edges that connect the vertices. So we specify what are the vertices and which vertices, which pairs of vertices are connected. And the main problem in practice is to get useful information about the structure, the inherent structures in this network. If I just give you vertices and edges, if this is an internet network, all you see is that there's millions of vertices and some of them are connected, but is there any structure in it? So here's an example. Let me give you an example of sorry. Yeah, this one. This is internet. Internet network, actually a very small part of it. The vertices, I believe in this case, are IP addresses, and there's connections with them. And if you look at, if we zoom in, for example, then you can see this beautiful families, maybe that these little stars are maybe routers that have the households, and maybe companies with bigger stars. And there are more connections in some parts of this network, and there are less connections in others, and there's beautiful structures like this. And this is what you would like to understand. This is what we would like to detect. Are there any particular parts of this network that are tightly connected, for example, or loosely connected? Another example. This is the Twitter, a part of the Twitter network. And there's Theresa May there, so it's a UK probably. Again, there are some structures here that are apparently present, some kind of clusters, communities that form. There's communities in particular, right? We would like to detect them and, let's say, partition the network into these communities. Understand what parts are more dense and what parts are sparser. But how can we do this if all we know is just which pairs of nodes are connected? It doesn't give us any information about density or anything like that. So that's a question. So this is the network. It's an undirected graph, and we need to understand how to deal with these graphs. We suggested to look at the baby model back in lecture 8. Suggested to look at a graph, at the network, as a random graph. Why is it even in principle a good idea? I don't know, but it's like a statistical mechanics idea, right? The graph of the internet or Twitter or Facebook are so huge, so large, just like molecules in this room. So maybe it's all deterministic, but we can model it as a random thing. Just like in statistical mechanics, we model the gas as random particles moving in random speeds and random directions. And then we get some better understanding. So that's a good idea, actually, to model a network.
I would also say that it's a good idea because it changes with time.
Why is it a good idea? And Olga, say it again.
Because it changes with time.
It changes with time, yes. It really is a random thing. Well, maybe not random, but it really is a dynamic thing. You don't know where the users retweet each other or where new IP addresses appear and so on and so forth. So it's a good idea to really do that. In fact, you mentioned a great property that we will not be working with time. It's not only a graph, but it's an evolving graph in time. And that's an extremely important property that we will not touch, but other people. And this is a very active area, how to model dynamic networks. Yeah. The very, very simple, like the ground level, the babyest version ever is a random graph that's called Erdős-Rényi. Erdős-Rényi. This is the simplest model of any network. Erdős-Rényi random graph G and P, which has n vertices, and we connect each pair of vertices with given probability P independently. So we have n users, and they can be friends or not friends. Each pair is a friend or not friends with probability P independently of any others. Here's an example of that. Let me show you this one. This is GNP, Erdős-Rényi model with 200 nodes, and connection is 140. And usually the graphs look like it's a big blob. There is no structure there. It's a big web that looks homogeneous, perfectly homogeneous. So the advantage, the pros of this model GNP is that it's an elegant model. It takes me just one sentence to describe it. It's very simple, simply organized. It's just two parameters, n and p. That's it. But this also is a disadvantage. The con of this model is that it is too simple. In particular, it's homogeneous. There is no communities. There is no information in this thing. Our goal is to detect the communities, and we start with the model that has no communities. That's not right. We should be making a little bit more sophisticated model, maybe. So how do we do that? How do we deal with that? How to model communities? What is a, again, it could be a baby model, but what would be the baby model, mathematical model of a network with communities? If we don't want exactly Erdős-Rényi, how do we, any suggestion?
Wait, but directly in Erdős-Rényi, if we take clusters, connected clusters, why is it not good as a model of a community?
What do you mean connected clusters? Sorry.
We take vertices that are connected, like we define the community as a set of vertices where each vertex is connected to every other vertex.
Mm-hmm. Yeah. So if I understand you, yes.
My question is, why is it a bad model?
Yeah, no, that's okay. Good idea. So lecture 8, let's see. So if if P is greater than log n over n, so basically if the average number of your friends is above logarithmic in the size, then everything will be connected with everything. The graph is connected. And then it becomes just a uniform homogeneous model. And we actually did this in lecture 8. We saw then everybody has the same number of friends. It's not interesting, no communities, everything is just. So P should be made less than log n over n. In this case, interesting structures do appear. And that's, let me actually show you back. Maybe I can find it. Lecture 8, I think. Yeah. Here we go. So this is Erdős-Rényi for smaller P, for P less than the connectivity threshold, log n over n. And then interesting structures do appear, but unfortunately, what happens is that there will be a giant component. This is a result of Erdős and Rényi in that paper from 1956. Even though the graph will not be connected, there will be one giant component. And by giant, I mean it has like 99% of the edges. And the rest of the edges will, the rest of the vertices that are disconnected will be either totally disconnected like this, or will form local trees, which is clear here. There's little parts. So again, they're not a good idea for a community. They're either like a huge community, maybe like Google community, and they're little tiny little microbloggers. So Erdős-Rényi doesn't really offer us a lot of realism in modeling the networks. How can we? Yeah, let's think. Based on Erdős-Rényi, where we connect each pair with probability P independently, how can we modify that to allow for communities to appear?
Well, the idea is to make maybe make weights to the vertices, so that some vertices are more like influential and they kind of have higher probability of.
Yeah. That's a great idea. So some vertices will be more influential and some vertices will be less influential. You're trying to rediscover here the so-called preferential attachment model, actually. So it's there. That's a very good idea. So some bloggers are more interesting and influential, and then they commit. Yeah, that's perfect. That's a wonderful idea. It will be a little bit more difficult than the one I'm going to suggest. But I'm going to suggest something very similar. Instead of making different importance of vertices, make different importance of edges. So put weights on edges. Namely, let's say we have boys and girls in the high school or something like this. And then let's say boys make friends with boys more likely, and girls friends with girls more likely than boys making friends with girls, just for the sake of this argument. So make this Erdős-Rényi graph, kind of Erdős-Rényi, but with different probabilities of connections. So boys should be connected with probability, let's say 1/10, girls with probability 1/10, boys and girls with probability 1/20, for example. So that will pretty clear that it will form clusters. The boys will be more tightly connected generally, girls will be more tightly connected, but across there will be less probability of connection. So that's the idea. So we can allow different probabilities of edges. So here we go. Let's say there is n/2 boys. There's n/2 girls here, and we will connect boys with boys. Every pair of boys will be connected independently. Still, everything is independently with probability P. And let's say girls will be connected independently with probability P, every pair of them. But every pair of boy and girl will be connected with probability Q, which is less than P. which means that in general, there will be more sparser intercluster, inter-community connections than inside the communities. And that's called, this model is called the stochastic block model. If you Google it up, you'll see like hundreds of thousands, maybe of papers on this, which we denote GNPQ. So we just allowed two probabilities, and here we go. That's a stochastic block model. Good, guys. Type me the questions. I'll finish this sentence, and I'll see what you're asking. I know you're asking, so keep going. And yeah, so here is the model itself clear. And then, yeah, and then here we go. Here's how what it looks like. I generated this model. Actually, my student generated this. Here, there's 200 edge, so there's 100 boys, 100 girls. Probability of inside community connection is 1/20, and inter-community connection over here is 1/200. And here we have a nice and simple baby model of a network with communities. And let me see what you guys are asking. Thank you for the questions. That's great. Yeah. Okay. How do we know? So, okay. So what's the question? I can model this. Now the question is, I generate this model and generate a graph. Sorry, I generate a graph with this model like this. Okay. And I'm giving it to you, and I'm not telling you. I'm not telling you who the boys and who the girls are. You just know who is connected with whom, who is friends with whom, and that's it. Your job is to determine to separate the graph into the two clusters, boys and girls. Well, up to the permutation, I guess. You will not know who the gender, but you'll still be able to separate. Maybe, or maybe not. Okay, so that was the answer to the question. We do not know who the boys and girls are, and our job is to actually to find out. So we do not know the clusters beforehand. And Olga is asking, it has to be an individual property of each vertex. I'm sorry, I lost the track of this. What has to be an individual vertex?
No. It was a suggestion, maybe how to resolve the previous question.
Yeah.
Actually, I have another one.
Mm-hmm.
You have shown this graph simulation, and I thought about bipartite graphs theory. Can it be applied, for example, here in a more probabilistic sense?
Yeah, exactly. That's a great suggestion, actually. This this model, where are we? This model where Q is less than P, it makes fewer connections across communities than within communities, right? But we could do the opposite. We could make Q much larger than P. Imagine, for example, that P is 0 and Q is something. And what will we see? What kind of the graph will we see? We see a bipartite graph, right? There will be a bipartite graph, meaning that nothing, because P is 0, nothing will be connected inside these clusters, and all of the connections will appear across clusters, like this. All of the graph will be like that. So this will be a mathematical model of a bipartite graph. But if you allow Q to be something, P not be 0, but maybe small, Q less than Q greater than P, then we will see some edges form here, but most of them will be across. So this is where Q is greater than P. Let's see where Q less than P, where the communities are tight. I think this is called the assortative model, and Q greater than P is called disassortative, I think. So you can Google up and you will see. So the stochastic block model, actually, it encompasses both things. It could be assortative, it could be disassortative. Either it should be tight clusters or it should be very loose clusters. It's a good question. Yeah. Anything else? Any other questions? Good. Okay, so that's our next job, is to learn how to cluster networks, how to find things, and the theory that we covered so far, especially matrix Bernstein's inequality, matrix Irving's, will be key to success here. Okay. Any questions? Anything? Any other suggestions? You asked great questions today. Thank you. Yeah, we can stop now, but maybe any idea how you can do this? Maybe forget Bernstein's inequality, just anything, just any method to cluster network to find the communities. Any suggestion how to do that?
Well, we could try to somehow modify usual clustering of the data points, but assign some kind of a distance on a graph, and then apply usual methods. But for that, we need to define the distance.
Yeah.
Distance is probably the number of friends.
Well,
no,
no, distance between the 2 points. Let's say, what's the distance from you, Pavlo?
This is number of common friends. Number of common friends. Yes.
What if it is 0? What if you and I don't have common friends? Then what?
I would say the shortest path, but
yeah, shortest path. So
like,
if you and I don't have any common friends, then maybe we have some chain of friends. You're friends with this, and that is friends with this, and that is friends with me. So the shortest path will define the distance. Yeah, so Olga is right. It's just the number of links that lead you to me. That will be the distance on the graph. Yeah, so it's called graph distance, actually. So we can define graph distance, and then what?
And then cluster in that.
Yeah, what method do you know to cluster?
Like k-means here, we have two clusters.
K-means don't work. No, k-means it requires linear structure, right? K-means takes arithmetic mean of something. So you should you add the points and then divide by n, right? It requires us to add
things. We have some distance from one point to another, yes, but maybe somehow we can adapt this approach to the graphs, somehow modify.
Yeah, well, right. The k-means is hopeless at the outset. We can't adapt k-means because it's really based on taking the averages. And you can't take averages. It has to be a linear space, linear structure, and these points are not in the linear space. But you're not far from truth. I think your thinking, Olga, is taking you in the correct direction. So adapt. We cannot adapt k-means. That's hopeless. What else can we do?
Maybe closest nearest neighbors.
Yeah, we can just grow closest nearest. So take from one point and then grow, like include neighbors. It doesn't work, unfortunately, in practice. Yeah, but it's a great idea, but it doesn't work. Because you don't know where to stop. You can grow, and then what? So there are two things. Actually, I'm not far from truth either, but let me show. So Olga is suggesting adapt k-means. Almost a good idea. A great idea would be to first geometrize the graph. We already put the distance, great. Then what you can do is to map the graph onto Rn somehow. So just try to put it geometrically, like I did on the plane. I already did it. I already put it somehow in the picture, right? So map it onto the plane and then apply k-means to that. That is a non-trivial approach. It's called multidimensional scaling, and it requires you to do the following. So it's an optimization problem. Find the points on the plane, or let's say in space. Find the points in RD whose pairwise distances resemble the graph distance as best as possible. Right. So you look at, let's say, the vertices are called xi's. So the distance between xi and xj should be very similar to the Euclidean distance between yi and yj on the plane. And then you just optimize the points so that they do that. And then you do k-means. So that's possible. I do not know if that will work nicely. I don't think it will work nicely. The reason is that the graph distance is usually is really not a Euclidean distance. It's not embeddable in the plane. It's something else.
I get it.
Yeah. So that doesn't quite work. The other idea was I actually like the idea. Who suggested that? To minimal. What was that? Something like closest neighborhood. Yeah. No. Closest neighborhood. Yeah, it's kind of a physical idea, grow the neighborhood. So what you can do is like this. Imagine you're pouring a liquid into the graph, and the edges are like little channels. So you pour in a liquid, and then the liquid will flow. But if there are clusters that are tightly separated, like this, then the liquid will find longer way to find its way into that cluster. And so eventually the liquid will flow and stabilize. But in the beginning, when I drop a lot of liquid, it will stay within the cluster where it is. Kind of, yeah. So because of the bottleneck from that cluster to the other. So we can do that physical modeling actually, but not with the liquid, but with a heat. So we'll heat one vertex and use a heat dissipation. And after a while, you will see how that, well, after infinity of time, everything will have the same temperature. But in the middle, there will be a lot of kind of bulb on one cluster, and that's how you find clusters. Now, doing this heat approach, it's the same actually. Well, the heat is what? The heat is a lot of particles moving. And it's the same as if I take one particle and let it move randomly. And if I move a random particle on the graph, that is a random walk on the graph, and that's a Markov chain. So mathematically, it's best to think of graphs as Markov chain, where I just move from one vertex. So it's like a page rank algorithm in Google. So I'm sitting here and I'm choosing one of my friends at random, and I go there. And I choose another, and from there I choose another friend at random and go there. And as we walk, the Markov chains can be, the Markov chains eventually mix, which means that the stationary distribution will be everything. But in the mesoscopic regime, which means that after a while, I will see that my distribution will be mostly sitting in the cluster, and that's how I find it. To find that without actually running things on a computer, without generating that, you can use a spectral theory. You can just take the transition matrix of the Markov chain and look at its eigenvectors, and that will be eigenvalues, eigenvectors, and that will be a good idea. The eigenvectors will actually tell you what communities are. But as soon as you think about eigenvectors of the transition matrix, then what you think is, well, why do we have to take some complicated transition metrics? We just take the adjacency metrics of the graph. Just take a matrix, 0, 1 matrix, and just put 1 if the ith and jth vertex is connected and 0 otherwise. Just a matrix that encodes the graph. You understand what adjacency matrix is, right? You just put 0 if the vertices are not connected and 1 if vertices are connected. The 0, 1 matrix. Symmetric, obviously. And take its eigenvectors, and to just run PCA on that. Just run PCA on the adjacency matrix, and that is a method that works. It's not the best practical method. I'll show you what the best are, but this is the first approach, and that is the one that we will actually cover. So it's just running PCA on this adjacency matrix. Good. Okay, I'll just stop talking now. Any other questions, guys? We went over time today. Yeah, great. Yeah, great, guys. You have very good suggestions. Think about other methods too, because I think I'm fixated on what I know. Maybe you'll suggest something else which is useful to cluster the graphs. Good. Let's see. I remember that I wanted to meet with Olga Moskovin. Olga, I think that was a plan to meet with you, right?
I guess so.
Yeah. Okay. Let's stay together after the class, and everybody else have a wonderful weekend, and we'll see you on Monday.
Yeah, thank you.
Thank you. Bye.
Bye.
Thank
Have a
you.
great-
Goodbye.
Have a great weekend.
Thank you, you too. And I'll stop recording.